All right, hello. This is the fourth and final lecture for Chapter 4. And we, of course, are going to be exploring oxidation reduction reactions. So this is the last reaction type that you'll be expected to analyze in Chapter 4. Okay, so what is an oxidation reduction reaction? An oxidation reduction reaction involves the transfer of an electron from one species to another. So always, in these kind of reactions, you have a transfer of an electron or multiple electrons. So just like our acid-base reactions always involve a transfer of a proton, our oxidation reduction reactions are always going to involve the transfer of an electron. Now we call them oxidation reduction because those two things are always going together. So oxidation is reflecting the loss of an electron, and reduction is the gain of an electron. So remember, matter is neither created nor destroyed. It is just being transferred from one form to the other. In this case, it is being transferred from the species that is oxidized to the species that is reduced. Right, so we have this nice pneumatic to use, pneumatic is different, oil rig. So oxidation is loss, reduction is gain. So I really like this little schematic that we have here. So you have a species, and before the reaction as a reactant, it has this electron. That electron in the reaction is transferred from the species that is oxidized to the species that is reduced. And as a result, you have the species in orange now in its oxidized form, and the species that was reduced in its reduced form. So again, they always go hand in hand, and this is the way that we represent them, is with these things called tie lines. And we'll get a lot of practice with this at the end of the chapter, and there's a lot of practice in your recitation, so don't stress it right now. But this really helps to show what change has taken place, where that electron has moved. So because they always go hand in hand, we often will call oxidation reduction reactions by this abbreviated term of redox reactions. Very exciting. So you'll hear me use both, know that they mean the same thing. Okay, so it shouldn't surprise you that if an oxidation reduction reaction is the transfer of an electron, that the formation of our ionic compounds is the result of an oxidation reduction reaction. So here we have solid sodium, and we have gaseous chlorine reacting. So this is what that reaction vessel looks like. And it's going to form our salt, right? And we know that the salt is an ionic compound and that it exists because we had a transfer of electrons from our sodium to our chlorine. So sodium lost electrons in this. Oxidation is lost, so we know that sodium was oxidized. And this is reduced. So we've already got some familiarity with this, and what we're going to see as we continue this lecture, and there's a nice video that I have posted on the Chapter 4 overview that I encourage you to watch too. Oxidation reductions are wildly important for life on this planet and for the way that we function and exist as human beings in our modern world. So the first example of an oxidation reduction reaction that you have seen before in your life but just may not have known that it was oxidation reduction is, I don't know why this isn't, so weird, is photosynthesis. So photosynthesis is the way that energy on our planet from the sunlight gets converted into food for all of our biosystems on this planet. So we have this intake of carbon dioxide and water in order to produce glucose and oxygen by photosynthetic species that contain chloroplasts. So in this reaction, we have the reduction of carbon dioxide, and we have the oxidation of our water. Now, which is really interesting. I won't get into it. Photosynthesis is so interesting. Take biochemistry. Do it. Another form of oxidation reduction reaction that you are likely familiar with or have studied before is cellular respiration. So cellular respiration is the way eukaryotes, complex organisms, multicellular organisms create energy. So you have probably heard of the electron transport chain that takes place in the mitochondria that produces a lot of ATP compared to strict glycolysis. So in cellular respiration, you have electrons being removed from more complex molecules and traveling down the electron transport chain until they meet the terminal receptor for cellular respiration, which is oxygen. So life couldn't exist without photosynthesis. We couldn't exist without cellular respiration. Both are redox reactions. Pretty cool, obviously important for you to know. Okay, so species can have multiple different oxidation reduction states. This is a kind of nauseating chart of the oxidation states that a species can exist in. So the oxidation states are things that are numbers that we assign to a species in a compound, and they're a tool that we use in order to be able to track the movement of an electron in a redox reaction. So these are just tools. It's not like the ionic charge that we've talked about before. And if you remember, it might have felt like kind of annoying at the time, but like when we write calcium, we always put the number first and then the positive sign. That is to differentiate the ionic charge from the oxidation state, right? Notice these would be written with the number first. So if you have calcium plus 2, that's the oxidation state. Calcium 2 plus, ion charge. Right? So these are tools that we use in order to assess the reaction. You do not need to memorize all of these values. There is a hierarchical rule list that we will use and that we'll get some practice with in this lecture. Okay, so this is the table that your textbook provides you with. So I'm actually just providing this here so that you have it in your abbreviated kind of notes for the chapter that I always have posted on Brightspace, but I prefer to use this version. So the rules here are hierarchical, which means that you have to wait for it. You have to follow this rule. It takes precedence over rule 2, rule 3, rule 4, rule 5, right? All of these are subject to rule 1 first. So rule 3 is more important than 4, 5, 6, 7, 8, 9. So it doesn't matter that group 6A normally has an oxidation state of -2 if it gets trumped by a higher rule. Okay, so one rule that is not on here, but that is implied, and it is 100%, you could call it like rule 0. It has to be held, is that the sum of the oxidation numbers must equal the charge of the molecule. Right, so if you have a charged molecule, like our nitrate ion, that means that your sum of your oxidation states has to equal -1. But for any species that does not have a charge, and that charge would have to be written for you, their oxidation numbers must add up to 0. Okay, so let's put some of that into practice and just kind of see what each one of these rules look like. Actually, I don't want that, I want you. Okay, so a pure element. What do I mean by a pure element? So this is the top of our hierarchy. Pure element's oxidation number is going to be 0. So examples there would be like iron. Iron is a metal. It can exist on its own, as we know, and its oxidation number would be 0 if it were in a reaction just as iron by itself. Another example would be our diatomic molecules. So even though there's 2 of them, each one of those hydrogens would have a oxidation number of 0, giving H2 an overall state of 0. Then we have O2, would also have an oxidation state of 0. So this is our pure element. So it's going to be compounds by themselves, or our diatomics are going to have that charge of 0. All right, so that's the first rule. Now, monatomic ions are going to have the charge of the ions. So if you had calcium 2+, the oxidation state, which I'll write in red, would be +2. This is also following our golden rule, which I will write in gold, if we can see it, that the sum, of your oxidation numbers must equal compound charge. So if our calcium is in its ionic form, it's already lost those 2 electrons, then its oxidation state is 0. Another example would be, okay, so we did iron before without a charge. Its oxidation state was 0. If it is iron +3, right, so it's lost 3 electrons, then its oxidation state would be +3. And that is an example of monatomic ions. If you have a group 1A metal, it is going to have a +1 oxidation number. So for example, if you had NaCl, the sodium oxidation state is going to be +1. It needs to have an overall charge of 0, so my chlorine is going to have a charge of -1. Right? But the first rule I have to obey here is that group 1A has a +1 charge. Another example would be potassium nitrate. All right, so this would be a +1. Now I have 3 of them. So I need to make sure that at the end, when I calculate all of the oxidation numbers, that the total value is 0. So the way that I like to remind myself to do that is above the individual atom's oxidation state, in this case, that would be +1, I write the total contribution of that part of my molecule. So each potassium is a +1 oxidation state. The total contribution to my molecule is +3, or my compound. So that means that my nitrate, or sorry, not my nitrate, my nitrogen has to be -3. So +3 plus -3 equals 0. This is an uncharged compound, so I am obeying my golden rule, my rule that rules them all. All right, next one. Let's take a look at fluorine. Okay, so if we have hydrofluoric acid, fluorine's going to be negative, making hydrogen positive, giving me an overall charge of 0. Right, so you see which one of these rules you have to apply, and then you apply. Let's do another one. So this is a kind of weird one. Fluorine here would be negative, which means chlorine has to be positive. We don't think of chlorine as typically being an electron donor, right? Because it is very electronegative, but fluorine is more electronegative than chlorine, and it will strip that chlorine. Okay, then we have our hydrogen. So hydrogen is going to be a positive one, so let's just look at like H2O, positive 1 for hydrogen. So the total contribution is positive 2, which means that the oxidation number for oxygen would be negative 2. Oxygen, this is the next rule, rule 7, is going to have a negative 2 charge that can be trumped by hydrogen. So that would be negative 2, overall charge, negative 4. Our charge of sulfur then would have to be positive 4, right? It needs to balance out the overall charge of those hydrogens. So going back to what I just said, if we had H2O2, hydrogen trumps oxygen, so that's plus 1. Total value is going to be plus 2 of our hydrogens. My oxygens has to balance. Remember, 6 is more important than 7, so my oxygen here would have an oxidation state of negative 1, giving us negative 2. Right? It's hierarchical, really important to keep that in mind. All right, then we have group 7A. So let's just say that's carbon tetrachloride. It's going to be negative 1. Overall charge, negative 4, which means that my carbon has to have a charge of positive 4. Oxidation state. Group 6A. Group 6A is going to have a charge of negative 2, so let's say it's PbS2. It's negative 2. Total charge of negative 4. What does that mean that my lead has to be? It has to be whatever it needs to be in order to follow or to obey our golden rule. So that's going to be a positive 4, because positive 4 plus a negative 4 equals 0. Okay, so that's just some kind of in the box looking at oxidation numbers and how we would assign them. But that's not really their biggest utility. We use oxidation numbers in order to figure out what has happened in a chemical reaction. So let me just drag this up here. So what we're going to do is you'll have a chemical reaction like the one between iron and zinc that's shown here, and you'll assign oxidation states, and from that you can determine what reaction has taken place, what species was oxidized, which species was reduced. Okay, so we have iron here and it's by itself. So what rule do we have to follow? Oh, let me roll this up. It's going to be rule number 1. It is a pure element. It is by itself. So it has an oxidation number of 0. And I like to just go reaction, reactant, product, product. So zinc has a charge of positive 2. So its oxidation number is going to be positive 2. This should say 2 plus. It's a little annoying, but that's okay. Next one, we have iron. I'll change our color because we're moving now to our products. Iron has an oxidation number of positive 2 because it is an ion, a positive 2 ion. And our zinc has an oxidation number of 0. So now what we do is we draw what are called tie lines. So tie lines are a way that we show the movement of those electrons. So I have my iron going from 0 to +2. So you can think of this as like a continuum, right? Where 0 is something that's totally neutral. And as your oxidation number goes down, you are going to be reduced. So if your oxidation number goes down, you were reduced. If your oxidation number goes up, you were oxidized. Why? Because if you lose electrons, oxidation is loss. You lose electrons, you become more positive, right? If you gain electrons, reduction is gain. You go down in oxidation number, you become more negative, more like an electron, which is a negatively charged particle. Okay, so in this case, our iron went from 0 to 2. So if you think of this as 0, this is 2, it went up. So we know that it is oxidized, right? It lost electrons. Specifically, it lost 2 electrons. Our zinc, change our color here, went from +2 to 0. So it went from positive to more negative, which means that it was reduced, which means that it gained electrons. So in this problem, you would probably be asked what species was reduced and which one was oxidized. And you would answer by saying iron is oxidized and zinc is reduced. All right, let's do another one. All right, so for this problem, we have our copper is going to have an oxidation number of 0. Our silver would have an oxidation number of 0. Now we want to look at these 2 ionic compounds. So remember, our ionic compounds are going to be this combination of silver and nitrate. And so we see that we have this monatomic ions are going to have the charge of the ion. So that means that my silver nitrate, which is going to be aqueous in solution, so we really have this aqueous silver, is going to have a +1 charge. Our oxygen would be my next rule to follow, so that's 2, 4, 6, right? Because I have 3 of them at a -2 oxidation state each, so that's -6. So that means that my nitrogen has to be a +5. Over here I have my copper. This is apparently copper 2 nitrate because we needed 2 nitrates to balance it. So same logic as we applied here. It is an ionic compound that's going to be free floating in solution. So these coppers are actually copper ions in solution, specifically copper ions with a +2 charge. And so their oxidation number would be +2. Then we have our oxygen, -2. We have 6 of them. No, yes, 6 of them. So -12. Which means that my nitrate, right, so we have -12 and we have a +2. So I have like this deficit of +10. So I need my nitrate, which I have 2 of, to equal +10. So divide that by 2 and you get a +2, or +5, excuse me. Right, so notice with our silver nitrate, we took +1 plus +5 is +6, -6 is 0. Now we have 5 times 2 is 10, plus 2 is +12, -12 is 0. All right, so let's clear this out of here. Oop. Why won't you work? All right, I guess I'll just have to resort to erasing. All right, so let's draw our tie lines and see what transpired. So we had copper went from 0 to +2. It became more positive, which means that it was oxidized, right? Which means that it lost electrons. And then we have our silver, which went from a +1 to a 0, right? It became more negative, which lets us know that it was reduced and means that it gained electrons. Right, so you really want to get a lot of practice with those because the more familiarity you get, the more instances that you see, the easier and more intuitive it will be. Get a lot of practice with that. Let me back up. Your recitation packet has a section on balancing oxidation reduction reactions, and you will not be expected to demonstrate that. So that is a skill, but I think because our textbook doesn't introduce us to half reactions, it's best just to leave that for an inorganic chemistry class if you take one. Okay, so the last thing that I just want to introduce with redox reactions is this kind of interesting terminology that you need to be aware of. So if a species is oxidized, it loses electrons and its oxidation state goes up. It is also known as the reducing agent. So a species that is oxidized is also, or readily oxidized, is also known as a good reducer, which is annoying, but that's the way it is. Likewise, if something is reduced, it gains electrons and its oxidation state decreases, and it is known as the oxidizing agent. So it is a good oxidizer. It causes something else to be oxidized. That means that it's really good at taking electrons. So oxidation reduction reactions at first can seem like pretty complicated, but you just need to practice those rules and really get them down, feel comfortable with them. And also you'll realize that there's kind of this flow to them where your key indication that a redox reaction has taken place is that you'll have a species by itself that then is combined in a more complex compound, or something in a more complex compound that then is reduced or is then on its own, right? So if you think about that first rule, if it's by itself, it has an oxidation state of 0. If it was combined with anything else, it's not going to have an oxidation state of 0. So that's a really good way to start to suss out if an oxidation reduction reaction has occurred, because one species was with something as a reactant, it's by itself as a product. It's a red flag that it's a reduction reaction. So the terminology here is just something to get a little familiar with. So combination reactions would be when you have those two species by themselves, like the sodium chloride that we saw at the beginning of this lecture, combining to form sodium chloride, right? We had sodium, we had chlorine gas, combined sodium chloride, two species by themselves, now they're together, redox reaction. Decomposition, if we were to reverse that reaction, we had sodium chloride broken apart into solid sodium and chlorine gas, that would also be a redox reaction, and that's called a decomposition reaction. Combustion reactions or oxidation reduction reactions, all combustion reactions have the form of a hydrocarbon, so that is a molecule that contains carbon and hydrogen in the presence of oxygen, and the products are carbon dioxide and water. Then we have a displacement reaction, which is where you have a species by itself, species together, and they swap. So one of them kicks the other one out, if you will. You can also have a double displacement reaction, which is going to look a lot like a precipitation reaction. So double displacement would take the form of like AB plus CD going to AD plus CB. That is called a double displacement. And that looks very similar to our precipitation reactions. So if you're in doubt on whether or not a reaction is precipitation, an acid-base, or an oxidation reduction, the way to figure it out is to assign oxidation numbers. If there is no change in oxidation number in a species, in any species in your reaction, from products to reactants, or reactants to products, then you do not have a redox reaction. It's something else. It's either precipitation or acid-base. So it's one of the things that students can find a little bit challenging in this chapter is just determining what has happened, right? So if you look at this first problem, we have calcium combining with the chlorate ion to form calcium chlorate. Now that would fit into two possible categories. We have two ions combining. So my first thought is that a precipitation reaction? Does this compound precipitate? The second question that I would have is it a redox, right? Because we had that combination reaction in the last slide. So the way that I would want to determine that is by looking at my handy dandy periodic table, and I see that yes, calcium chlorate is, calcium carbonate is insoluble, so a precipitation is going to form. Their charges are the same, right? So this is still -2 for my oxygen, 2, 4, 6, -6. Calcium is +2. That means that my carbon has to be a +4. Notice that's going to be the same over here. So that's -2, 2, 4, 6, -6. You're +4, giving me an overall charge of -2. And here, an ion has its charge. So my calcium still is a +2. My carbon is still a +4. My oxygens are still -2. There is no redox reaction, right? No change in oxidation number. However, this does form a solid, so this is a precipitation reaction. Here I have ammonia, my hydrogen ion, forming the ammonium ion. +1 gives me a total charge of +3, right? -3, +1, giving me a +4. This is going to be -3 still. Oh, sorry, that went away, but because it has this positive sign overall. So no change in oxidation number. Ammonium is itself a soluble ion. It's not going to be a precipitate. It has nothing that it's combined with to precipitate with. However, we do have a proton transfer. So this would be acid-base. All right, we have calcium fluoride. Species by themselves. Now we have negative, this is -2. Our calcium is going to have to be a +2. So we have a change in oxidation number. Remember that red flag that I told you? These species were by themselves. Now they're in a compound. Oh, that's a really ugly circle. So that it was a good indication that a redox occurred. Right? Fluorine went from 0 to negative. So that means that fluorine was reduced and calcium was oxidized. All right, this next one kind of looks like we have hydrochloric acid. Maybe that is a acid-base reaction. So the only way to really know for sure if it's acid-base or it's oxidation reduction is to assign oxidation states. 0, 0, negative, -2, +2, negative, positive. All right, zinc went from 0 to a +2. That means that its oxidation number went up, so it was oxidized. Right, it gained it lost electrons. Our hydrogen went from positive to negative, which means that it gained electrons. and was reduced. So just to recap, we have a redox, we have a redox, we have acid-base, and we have a precipitation. Precipitation is going to be pretty obvious. It's ionic compounds coming together, dissociating, forming an insoluble compound. Acid-base follow that proton. If you're not sure, assign oxidation numbers and see if they change. Redox, something by itself coming together, something by itself now it's part of a compound, right? So this would be that single displacement. All right, cool. That is it for chapter 4. So make sure that you get a lot of practice with each one of these reaction types. We definitely went the most in depth with precipitation, so you want to feel very, very comfortable with that and get the big ideas from oxidation reduction and redox. Any of the reactions that we did today, I would expect you to be able to evaluate on your midterm. Whoa, class is half over. That's crazy. All right.